All right, for part C, we're going to apply the same strategy. First of all, I'm going to construct an equals f of n, which is arctan n divided by n squared plus 1. And here I can grab f of x as arctan x divided by x squared plus 1. So since n starts from 1 here, so why don't we go ahead and then say like x is greater than or equal to 1. But we can also always play with the x values as the way we did in part A and part B eventually. Okay, so let's check all three conditions here. Is f positive? Okay, well, the bottom is always positive because it's the square of x plus 1, and no matter what x is, it's positive. An arctan function, if you remember from calculus, check the range, in fact, of arctan, and for x is greater than or equal to 1, arctan is always positive. So you can go ahead and conclude that this is positive for x is greater than or equal to 1, check mark. Okay. Is f continuous? Well, f is the quotient of two continuous functions in their domain, obviously, but polynomials are always continuous. Arctan is continuous, and for specifically x is greater than or equal to 1, yes, f is a continuous function. And you're using our skills from calculus, obviously here, and in number 3 as well, right? Showing that f is a decreasing function is to look at the first derivative of the function as we did in the previous cases. So why don't we go ahead and then look at f prime, okay? F prime, and then depending on the sign of f prime, you will deduce about decreasing, increasing behavior of the function. All right, so f is a quotient. So let's look at f prime by using the quotient rule. Quotient, we can also use the derivative formula card, by the way, in this section because we're taking the derivatives and so on. You may not remember the derivative of the arctan function, so check the derivatives formula card. So arctan has the derivative of 1 over x squared plus 1. So this is the derivative of the first term times the bottom. So the derivative of the top, which is the derivative of arctan, times the bottom, minus, keep the top, arctan x, and multiply it by the derivative of the bottom, which is 2x. And all divided by, this is all divided by the bottom squared. Okay. All right, so let's simplify this. So 1 over x squared plus 1 times x squared plus 1, so they cancel out, so it's just 1. 1 minus 2x tangent arctan x, right? Arctan x, arctan x divided by x squared plus 1. And then again, remember, we were analyzing x's to be greater than or equal to 1. So one way to show that this is negative is just to graph this function if you don't know much about arctan. So graph the function starting from x min 1, x max to be like a large number, like 20, 50, 100, just to see that, just to make sure that this is less than 0, okay? We're completely safe here because x is greater than 1, so this number is almost about 2, and arctan is always taking bigger values. So you're safe here saying like this is negative for x is greater than or equal to 1. Okay, but again, if you're not really feeling confident about it, graph this function starting from x min to be 1, and you will see that you are going to be below the x-axis. The graph is going to stay below the x-axis. Okay. So going back to the discussion here, that f prime is negative, so f is a decreasing function. So all three conditions of the integral test are met. So then we're going to go ahead and then look at this integral here, this improper integral. Okay. So guess what we're going to use to integrate this. So at this moment, you can pause the video and then check or explore what technique we can use. But in the next slide, I'm going to show you the technique that I'm going to use. All right. As always, I convert this improper form into the indefinite form because first we have to integrate this, and we can worry about the limits at the end. So I'm going to use the u substitution here. U equals arctan x, so that du is the derivative of arctan, which is 1 over x squared plus 1. So du is dx over x squared plus 1. And that's awesome because dx over x squared plus 1 is part of the integration here. So this integral becomes u times du, and this is u squared over 2. I don't need to worry about adding plus c because eventually I'm going to go back to the improper integral. So this is equal to arctan x squared over 2. Okay? So once you're done with this integration, so you can go ahead and say that, let me just claim this part, and then this integral is equal to tan x squared over 2, and lower limit is 1, upper limit is infinity. And remember that the upper limit infinity is going to be written in terms of a limit. So in other words, when you plug in the upper limit, it's going to be in the limiting sense. Limit as b approaches infinity, arctan b squared over 2. Again, this is me plugging in the upper limit. And then the lower limit is going to be what? Arctan 1 squared over 2. All right, so you can now think about this limit. Let me just continue from here. So arctan infinity squared over 2. So arctan for very large values of b. So then you can think about like whose tangent is infinity. Okay, so then you can use your calculator, but calculator may not provide you anything because you can't really plug in infinity over there. But you can look at the behavior of tangent. So whose tangent could be infinity in its principal domain. So that should be pi over 2 because tan pi over 2 is like 1 over 0 type behavior. So this would be pi over 2 squared over 2. And then the other one is arctan 1, for which you can use your calculator. Tangent pi over 4 is 1, so arctan 1 should be pi over 4. So pi squared over 16 over 2. And if you do the calculations, this will take you to 3 pi squared over 32, which is finite, right? Finite. So the integral term is finite. Then I can go back and say that this integral is convergent. So is the infinite series. Okay. Arctan n divided by n squared plus 1 is convergent. I can go back here and conclude that this is a convergent infinite series. Okay. Again, we checked all three properties of all three conditions of the integral test to be met, and eventually we look at this improper integral. So this is a very long solution, right? So because you're checking all three conditions, you have to be very rigorous. You have to sort of like justify each step carefully. I think we're left with part D, so why don't we move on to part D.